This is just an old photograph. A bridge, black and white, probably 1890 something. Men standing on it, horses crossing it, nothing unusual. The kind of image you scroll past in a history book without a second thought. Except, there is something wrong with this bridge. Look at the arch. Look at the curve of the stone. Look at where the weight is distributed across the span. Modern structural engineers who have seen this photograph don't talk about it the way you'd expect. They don't say it's impressive for its time. They say it should not be standing. Not because it is old, because the math we use today with computers, with simulation software, with 100 years of accumulated structural knowledge, the math says that arch is carrying loads it has no right to carry, that it should have failed a century ago. And yet, there it stands. So the question is not why it hasn't fallen. The question is, what did the people who built it know that we don't? Old photographs are not just historical records. They are crime scenes. And when engineers look at them, really look, they find secrets buried in plain sight. Techniques that predate our understanding of them by centuries. Solutions to engineering problems we didn't even know were problems until we tried to replicate them with modern tools and failed. This is that story. Most people look at an old photograph and see the past. Engineers look at an old photograph and see a puzzle. Because every structure and every historical image is a data point. The angle of a wall, the spacing of stones, the depth of a foundation visible in the foreground of what was meant to be a portrait, the thickness of a timber beam caught accidentally in the corner of a construction scene. None of it was documented for engineers, all of it speaks directly to them. In the last 20 years, a specialized discipline has emerged, forensic structural analysis of historical photography. Researchers at universities across Europe and North America have been systematically digitizing thousands of 19th century construction photographs, running them through photogrammetry software that extracts precise three-dimensional measurements from two-dimensional images, and comparing what they find against modern engineering standards. What they keep discovering is stopping them cold. Again and again, structures that should be on the edge of failure or past it are not just standing, but performing flawlessly, often carrying loads far heavier than their original designers could have anticipated. Traffic that didn't exist when they were built, vibrations from vehicles that wouldn't be invented for decades, climate stresses from a warming atmosphere their builders never modeled. Somehow, they accounted for all of it. Not because they were lucky, because they were applying knowledge we are only now beginning to fully decode. The Romans built arched aqueducts 2,000 years ago that are still standing. Not as ruins, as functioning structures. Some still carry water. The Pont du Gard in southern France is 160 feet tall, built entirely without mortar in its upper tiers, and it has not moved measurably in 2 millennia. For a long time, the explanation was simple. Romans overbuilt everything. They used so much stone, so much mass that the structure survived by sheer bulk. Then, researchers started feeding photographs of Roman arch construction into modern load simulation software. And the overbuilding theory collapsed. What the software revealed was not brute force. It was extraordinary precision. The Romans had empirically discovered, through centuries of trial, catastrophic failure, and accumulated observation, a principle that structural engineers would not formally articulate until the 19th century. The catenary curve, the precise mathematical shape that a hanging chain naturally forms under its own weight. Flip that curve upside down, and you have the ideal arch, the shape that converts every downward force into pure compression, pushing outward and downward through the stone rather than pulling it apart. The Romans did not know the equation. They did not have calculus. They did not have the language to describe what they were doing. They had eyes. They had generations of watching what worked and what didn't. And they carved that knowledge into stone so precisely that a computer running the numbers 17 centuries later comes back with the same answer. The photographs caught it. Measurements taken from 19th century construction images, when Roman methods were still being actively imitated, show the same curve, again and again, passed down not through textbooks, but through the hands of masons who had learned from masons who had learned from masons, all the way back. Here is a photograph from the construction of the Brooklyn Bridge, 1872. It shows the interior of a caisson, an enormous pressurized wooden chamber sunk to the riverbed so workers could dig foundations in the open air while the river pressed down above them. What it also shows, if you look closely at the background, is the wall thickness of that caisson, and the angle of the support timbers inside it, and the approximate air pressure the workers were operating under, calculated from the depth of the excavation visible in the image. When modern engineers modeled those dimensions, they found something extraordinary. The caissons were operating right at the absolute limit of what the wood could structurally handle, not over-engineered, not wasteful, but precision calculated to the edge of the material's capacity. The men who designed them, working with slide rules and hand calculations, had landed within a few percentage points of what the most sophisticated modern analysis would recommend. Without computers, without finite element analysis, without any of the tools we consider essential to modern structural engineering. How? Part of the answer is something engineers call embodied knowledge. Understanding that lives in the hands and eyes of experienced builders, not in textbooks. The lead engineer on the Brooklyn Bridge caissons, Washington Roebling, had spent years before the project studying foundation techniques in Europe. He had watched failures. He had measured what survived. He carried that library in his mind, and when the time came, he drew on it with a precision that modern simulation has repeatedly confirmed. The photographs are the evidence. The measurements don't lie. In the 1990s, a team of material scientists in Britain began analyzing samples taken from medieval cathedrals, specifically from the mortar used in their construction. What they expected to find was crude lime mortar, the standard material of the era, known for its relative weakness compared to modern cement. What they found instead was something that shouldn't have been possible. The mortar in several of the oldest surviving cathedrals, structures approaching 9 centuries old, contained a microscopic crystalline structure that had continued developing strength for hundreds of years after the initial pour, not weakening over time the way modern cement does, getting stronger. The material was still actively binding, still growing denser, still increasing in compressive strength nearly a millennium after it was mixed and applied. Modern Portland cement, the foundation of virtually all contemporary construction, reaches its design strength in about 28 days. Then it begins a slow, irreversible decline. It carbonates, it cracks, it weakens. It is why modern concrete structures have design lifespans of 50 to 100 years, while medieval cathedrals, built from materially inferior ingredients by any standard modern metric, are still standing after 900. The key ingredient, identified in part through analysis of construction photographs that showed the texture and consistency of freshly applied mortar, was volcanic ash. Specifically, a material called pozzolana, sourced from volcanic regions and mixed into the lime. The Romans had used it. Medieval builders inherited the knowledge, often without fully understanding why it worked. They knew it made the mortar better. They had seen it with their own eyes. They kept using it. Modern researchers are now reverse engineering that formula, not to replicate it exactly, but to understand the principle that a material which continues to strengthen over time rather than decay is the most durable construction material ever used. And we lost the recipe for centuries. It was sitting in the walls the whole time. We just had to look. There's a comfortable story we tell ourselves about progress. It goes like this. Knowledge moves in one direction, forward. Each generation inherits everything the previous one knew, adds to it, and hands something larger forward. The arrow points up. Always. Old photographs break that story. Because what they reveal over and over is that knowledge is fragile. It does not automatically transfer. It lives in people, in practices, in traditions of doing and watching and adjusting. When those people die without passing it on, when a trade is disrupted, when a civilization collapses, when a material supply chain is cut off, the knowledge does not survive in books. It survives in the structures themselves, encoded in dimensions and curves and compositions that the people who built them could not have explained in words. Every old bridge still standing is a message in a bottle. Every cathedral vault that has not moved in 800 years is a transmission from people who knew something, deeply and practically, that we are still working to decode. The photographs are how we read those messages. A two-dimensional image, taken by someone who had no idea they were documenting a secret, processed a century later by software that extracts measurements accurate to the millimeter, analyzed by engineers who suddenly understand, for the first time, why something that should not work does. That is not history. That is archaeology of the mind. Go find an old photograph, any old photograph of a building, a bridge, a wall, anything built by hand before the age of computers. Look at it differently now. The person who built what you are looking at did not have simulation software, did not have material science databases, did not have centuries of peer-reviewed structural research to draw on. What they had was observation, memory, the accumulated embodied knowledge of everyone who came before them, pressed into their hands through years of apprenticeship and practice. And what they built has outlasted the computers we now use to study it. We are not smarter than the people in old photographs. We are differently equipped. And the things they knew, the deep, practical, experiential knowledge that lived in their bodies and not in any book, some of it we still have. Some of it we rediscovered, and some of it, if we are not careful, we will spend the next century finding again. In the cracks of bridges that are starting to fail, in the walls of modern buildings that are not aging the way their designers expected, in structures that last 50 years when their ancient predecessors lasted 500. The secrets were never really hidden. We just stopped knowing where to look. Anyway, I'm the owner of this channel, digging into the things that have always been in front of us, the structures, the photographs, the materials that are still telling their stories to anyone willing to slow down and actually look. If this one changed the way you see the world a little, subscribe, because next time we find another secret hiding in plain sight. I'll see you there.